Okay, so see what we are trying to study now at this stage of the course is the so called good functions that you can define on a variety, okay, and actually these good functions are called as regular functions, okay, and you know we have defined so for any variety or a quasi-affine variety in affine space, so if I call that as x is either a closed irreducible subset of some affine space, or I can take an open subset of course non-empty open subset of such an irreducible closed subvariety, that is an irreducible closed subset of some affine space. Then we have defined this operation O. This operation O gives you O of x in this case, and in this case it gives you O of u. And what is O of x? O of x is supposed to be the ring of regular functions on x, okay. O of u is similarly the ring of regular functions on u. So here what I am having on this side is affine or quasi-affine varieties. These are the objects on this side, okay. So an irreducible closed subset of affine space is called an affine variety, if you recall, and an open subset of non-empty open subset of such an affine variety is called a quasi-affine variety, okay. And for an affine variety or a quasi-affine variety, I defined the ring of regular functions to be functions which can be locally written as quotients of polynomials, okay. So what it means is that, see, your whether it is x or whether it is u, they are all sitting inside an affine space, and on the affine space I have natural functions given by polynomials in the right number of variables, okay. So if you give, so in this case if it is an, I am taking polynomials in n variables, and you give me a polynomial in n variables, that gives you a function from affine space into the base field k, okay, which of course just to remind you is always an algebraically closed field, and so any polynomial here gives you a map from an to k, okay, and that map can be restricted to any subset. So such a map can be restricted to x, such a map can be restricted to u, okay. And what we are saying is that we are saying that if you take two such polynomials, okay, and suppose I take the quotient of these two polynomials, and suppose I restrict this quotient to a subset where the denominator polynomial does not vanish, then that will also give me a function from that subset into K, okay, and its functions like this which I am calling as regular functions. So more generally a regular function is something that locally looks like a quotient of polynomials, okay. So in the right way to say it is that a regular function is something that it's a function which is got by which is locally a quotient of polynomials, and it's gotten by gluing such quotients, okay. And of course because of the quasi compactness of the Zariski topology, you know that this gluing can be done on just on a finite number of basic open sets, okay. That's something that we have seen last time. And in fact what we proved was, we proved that you know that whenever the variety is whenever X is isomorphic to an affine variety, okay. So I am again making a statement which is kind of a retrospective kind of statement. It's a futuristic statement in the sense that I have not defined what is meant by a isomorphism of varieties. So it's very strictly not correct or pedagogically sound for me to tell you, give a statement like let X be isomorphic to an affine variety, but assume it for the moment, okay. So the fact is that whenever a variety or so if X is already a irreducible closed subset of affine space, it's already an affine variety by definition. But if you take an open subset of such an affine variety, the beautiful thing is that it may or may not be an affine variety. What I mean by that is that it may or may not be isomorphic as a variety to another variety which is affine. So both cases happen. So there are special cases when you take u equal to you take X equal to if you take X equal to an, okay, and if you take u to be the basic open subset defined by the locus of points where a polynomial h in the right number of variables n variables does not vanish, then you know that this is actually an affine variety in the sense that this can be identified as a closed subset of an affine space of dimension 1 more. We have seen this, and in this case what happens is that even though u is only a quasi-affine variety in an, it is actually isomorphic to a variety in an plus 1. So in that sense u is not only a quasi-affine variety, but it is also an affine variety. It's not an affine variety in an, but it is an affine variety in an plus 1, okay. And on the other hand, you know, if I'll give you if you take this a statement like this, if you take an if you take a situation like this, take X equal to an and take u to be just the complement of the origin, okay. So you take an minus the origin, okay. Now this is also an open subset of an affine variety, and the fact is that, of course, the fact is that if n is greater than 1, this can never be isomorphic to an affine variety. It's a fact that we will see later, okay. This cannot be isomorphic to an affine variety, right. So there are open subsets of affine varieties, namely there are quasi-affine varieties which can be isomorphic to affine varieties, and there are quasi-affine varieties which cannot be isomorphic to affine varieties. And the point is that whenever a variety or a quasi-affine variety, especially whenever you take a let me begin like this. If you take an affine variety, okay, namely it's already an irreducible closed subset of some an, if you calculate the ring of regular functions, okay, then I proved last time that this is isomorphic as k algebras to the ring of polynomial functions, the ring of coordinate functions, the so called affine coordinate ring of X, which is defined to be just the affine coordinate ring of the full affine space in which X is sitting modulo the ideal of X, which is a prime ideal. So this is a finitely generated K algebra, and this is how I define the ring of functions on an irreducible closed subset. Okay, and the fact is that if X is an irreducible closed subset of an, then the ring of regular functions is naturally isomorphic to the ring of to this ring, the affine coordinate ring of functions that come out of polynomials. Okay, so what you're saying is, you're saying the following. So what does it mean? What it means is, if X is an irreducible closed subset of some an, then a function on X which is gotten by locally gluing quotients of polynomials is actually represented globally by a single polynomial function. Mind you, what are the elements of Ax? The elements of Ax are just the cosets of, the elements of Ax are just cosets here. This is a quotient ring, these are cosets. So an element of Ax is written as f bar, where f is an element of the affine coordinate ring of a affine space, namely f is just a polynomial in n variables, and f bar denotes the coset f plus ix. Okay, and the fact is that this f plus ix also defines a function on X. What is that function? It is just f restricted to X. You have, if you take an f here, it's a polynomial in n variables, so it's a function on a affine space, and X is after all a subset of a affine space, so I can restrict that polynomial function to X, and the resulting function on X is not f itself. It is a restriction of f, but it can also be represented by a g such that the difference f minus g is in the ideal of X. So writing a function here as f bar means that you are writing it up to the ideal of X, because if you have a function on X and you add to it a function that is identically 0 on X, okay, then the resulting thing is also going to give you the same function on X. Okay, so the function on X is of course a polynomial function on X is of course a polynomial function on an up to an element of the ideal of X, because the polynomial functions in the ideal of X, when you restrict them to X, they are going to give you the 0 function. Okay, and what does this isomorphism signify? This isomorphism signifies that you give me, if you take an irreducible closed subset of a affine space, then a function on that with values in K, if it is obtained by locally gluing quotients of polynomials, then it can be represented globally by a polynomial, as the restriction of a single polynomial function. That's what it says. And in particular, if you take X equal to an itself, what this will tell you is that if you take a function on all of a affine space which is locally the quotient of polynomials, then globally it has to be a polynomial, and that polynomial has to be unique, because in that case you will get an isomorphism of Ox, namely OAN with AAN itself, because IAN will be the 0 ideal. Okay, so that is the significance of that is the significance when you get an isomorphism, when you apply the O and the A. Okay, mind you can apply O, and A has been defined only for some certain special objects on this side. Okay, so if you remember, if you take a basic open set like this, okay, then I have defined A of that basic open set, the functions on that basic open set, to be just the localization of the functions, the ring of functions on the ambient space at H. So, and this is very simple. When you take a ring and you put a subscript saying you are localizing at that element, it means you are just inverting that element, and that makes sense because on dh, h does not vanish, so 1 by h and all powers of 1 by h are also valid functions on dh, and therefore a general valid function on dh will be some polynomial by a power of h, and that's exactly the kind of elements that you have in this localization. So we made this definition, okay, and in fact I justified that this definition is correct in at least I gave 3 partial justifications as to why this definition is correct. Of course, you know, one justification was that it's correct to invert h because h is not 0 on dh, which is the locus where h is not 0. Therefore a general function on this should be some polynomial divided by a power of h, okay, which makes sense. And when you collect all these things together and identify them properly, you will get the localization at h. That's one justification. What's the other justification? The other justification is that dh is also, as I told you, an affine variety because it can be identified with a closed subset of an plus 1. So you know this dh, if you recall, this d of h which sits inside an, okay, can be identified with the 0 set of hy minus 1 in an affine space of dimension 1 more, okay, where y is the extra coordinate that you are adding, okay, and this identification comes because of the projection map from an plus 1 to an. If you restrict it to this closed subset, you will get this. And what is, so you know, if you believe, I asked you to check that it is a matter of topology, to check that this identification is not only bijective, it's not just a bijective map of sets, but it's also a homeomorphism of the Zariski topology, which I hope you have checked, okay. But the fact is, you can go one step further. In fact, this is an isomorphism of even varieties, okay, and that's again a statement that we'll have to fix up later on when we come to the notion of isomorphism. But if you believe that, then then it tells you that since this is an irreducible closed subset of an affine space, this is an affine variety and this is something that's isomorphic to an affine variety, and therefore it's correct to define a of this to be the same as a of this, and the a of this is actually isomorphic to because of properties of localization in commutative algebra. A of this is precisely this, okay, because a of z of hy minus 1 is just a of an plus 1 divided by hy minus 1, which is the ideal of z of hy minus 1 because hy minus 1 is an irreducible polynomial, and this is actually isomorphic to a of an localized at h, okay, because this is k x1 through xn comma y by hy minus 1, and that is isomorphic to k x1 through xn polynomial ring localized at h, okay. This is a property from commutative algebra, and I was just trying to tell you that this isomorphism between these two rings is actually a commutative algebraic translation of this isomorphism of varieties, okay, and therefore I told you that's the justification as to why you can define a of d of h to be this, okay. That was the second justification, okay. And the third, there was yet another justification that I gave, and that justification was, the third justification was that if I take this a, so you know, it's the third justification is that whenever, for example, I start with an, okay, I go to a of an, if I take max spec I get back an, okay. So which means, so I'm just saying a max spec of a of an is the same as an, that's just the Nullstellensatz ansatz, if you really, but it's not just the Nullstellensatz ansatz as a set theoretic bijection, it's actually, I told you to check that this is even, in fact we checked, I think we actually checked that this identification of max spec of a of a and k, which is the set of maximal ideals in a of an with the Zariski topology for the maximal spectrum, which is induced by the Zariski topology and the prime spectrum, that with that topology max spec of a of an and an itself are homeomorphic. And again, let me go one step further, we will see it is a fact that this it's not just even a homeomorphism, it's an isomorphism of varieties in the most general sense, okay. So the fact is that similarly if I take an irreducible closed sub x, then we checked that if you take max spec of ax, then that is isomorphic to x itself. At least you must have checked that it's homeomorphic to X topologically, okay, but the fact is it's even isomorphic to X, okay. So the moral of the story is that somehow if something is affine, if you then you define the A of that, okay, and then if you apply max spec you should get back that thing, okay. So the fact is that if I take DH, if I apply A of DH, if I apply A to that I get A of DH, which is this, okay. If this is the correct definition, if I take max spec of this I should get back DH, and that is again a fact. I asked you to check at least topologically that you get it back, okay. So these are three justifications as to why this is the correct definition. But then here is yet another definition. For DH I can define O of DH, okay, and then it's a fact that O of DH turns out to be isomorphic to this, okay. So this is part of this philosophy that I was trying to tell you, that whenever something is affine, if you apply O to it and you apply A to it, A is always defined whenever something is affine, okay, and O is defined whether something is affine or not. And the fact is that the characterization that something is affine is given by the fact that when you apply O to it and apply A to it you should get the same thing. If you get the same thing, then and only then is that thing affine, okay, that is then and only then is that object and can realizable as an irreducible closed subset of some affine space, okay. So the fact that an object can be realizable as an irreducible closed subset of affine space, okay, is captured in checking whether O of that and A of that are isomorphic, okay. And I told you that, well, so if I take O of u, okay, I should not say O of u is not O of, so in this case if you take affine space minus the origin, I should not say O of u is not isomorphic to A of u. The fact is that I don't define A of u because I know it's not affine, okay. So A is somehow defined only in cases where things are affine, okay. And the fact is that for all those things that are affine, if you apply O also you will get the same result as you would get when you apply A, okay. Now yeah, so this is the story so far, alright. And so I was trying to just tell you that so here I should say here u is not affine, okay. U is not affine if n is greater than 1, okay. By that I mean u is not isomorphic to any affine variety provided n is greater than 1. Of course if n is 1 then you are going to get A1 minus the origin, and A1 minus the origin is affine because it is just d of x. What is d of x? D of x is the set of points where x does not vanish, and the set of points where x does not vanish on A1 is precisely A1 minus 0. So when n equal to 1 it is actually affine because it is a d of x, and all I am trying to say, so when n is 1 it is actually even basic open affine, okay. But when n is greater than 1 this is very far away, it is not even affine, okay, it is very far away from being affine, right. So alright, so now somehow now let me go back and try to tell you that in all these things I have been using this statement that some variety is isomorphic to some other variety, okay. So I have to define what an isomorphism of varieties is, and in a general philosophy the general method to define an isomorphism is to define a morphism which has an inverse which is also a morphism, okay. This is how you define an isomorphism, alright. So basically isomorphisms can be defined if I can define morphisms, and so what I am going to do next is how do I define morphisms, okay. So So let me make that statement here. So so let me put that as a title here, morphisms of varieties. So by varieties I mean either affine varieties, affine or quasi-affine varieties. Okay, how do I define what a morphism is? All right, now to understand this, let me give you let me go back to something more basic. Let me go back to topology. Okay, so see, let me take so motivation is let x, y be topological spaces, okay, and let mod x, mod y be the underlying sets. Okay, so you see what I am trying to do. Don't confuse mod x with the cardinality of x, which is the usual notation. Okay, so here for me mod x is not the cardinality of x and mod y is not the cardinality of x. When I write mod x I mean throw away the topological space structure on x and think of x only as a set. So mod x is just x as a set, mod y is just y as a set. Okay, now what I am going to do is there are two categories. There is a category of topological spaces and there is a category of sets. Okay, so in the category of sets the objects are sets and the maps. So just to recall, a category very naively basically consists of two pieces of data. One piece of data specifies the so called objects of the category and the second piece of data is the maps between these objects, maps with certain properties, and that is why the word morphisms is also used instead of just maps. Okay, so every category is specified by defining what the objects are and what the maps are. Okay, so when I say category of sets, the objects are sets and the maps are just maps of sets, okay, just functions from one set to another without any other properties. When I say category of topological spaces, the objects are topological spaces and what are the maps? The maps are not just maps of sets but they have to be continuous maps. Okay, and you can go on like this. For example, if you take the category of rings, the objects then are rings and the maps are not just set theoretic maps of rings, they are ring homomorphisms, okay, and so on and so forth. Okay, but I am only interested in these two categories with respect to these two guys. So if you take the object x, okay, and if you take the topological space x, then I have the corresponding underlying set mod x, okay, and if you give me the topological space y, I have the underlying set mod y, okay, and then well if you give me another topological space z, okay, then I will again get the set mod z, okay, and now well you see I start with so I do the following thing. If you give me a map f from x to y of topological spaces, okay, then I will get this map mod f, which is a map of from mod x to mod y, and the point about mod f is that I've forgotten the continuity of f. Here f is a map, is a morphism from x to y, it's a morphism in this category, so it has to be a continuous map, whereas if I take mod f I am just looking at the map as a set theoretic map, okay, and then well if you give me any map g, any continuous map g from y to z, then I get the composite map which is first apply f then apply g, and that's, and composition of continuous maps is continuous, therefore if g is continuous then f followed by g is also continuous, okay, and the corresponding diagram here will be, here I will get a mod G, and here of course I will get mod of G circle F, which is of course mod G circle mod F. I am simply forgetting the continuity here, alright. And see the fact is that there is a functor like this, and this functor is called the forgetful functor. It is a functor that forgets the topological space structure, okay. It is called a forgetful functor. We all because you are forgetting everything connected to the topology. You given a topological space, you are attaching to you're just associating to it just the underlying set, and given a continuous map of topological spaces, you are just associating to it the underlying set theoretic map, okay. Now what you get from this diagram is the following. You get, so you know, let me give some symbols, okay. So let me do that here. So you see what I am trying to say is, you have a home, okay, or let me not write home, I think home, alright. So let me use MOR. So this MOR is supposed to be abbreviation for morphisms. So when x and y are objects of a category, more x y is a set of morphisms from x to y, okay, in that category. So you see, if you have morphisms from, if you take morphisms as topological spaces from x to, well, so let me do the following thing. So I will do the following thing. I will take morphisms as topological spaces from y to z, okay, and if you give me a morphism of topological spaces from y to z, namely G, I get a morphism of topological spaces from x to z, which is G circle F, and this map which is going in the reverse direction, one writes this as F star, okay. This is called the pullback of morphisms, okay. It is very simple. You have two objects in a category, okay, you have a morphism between them, and what you are doing is, given a morphism on the target, you compose it with this to get a morphism on the source. So a morphism, a morphism from one object to the other object pulls a morphism on the target to a morphism on the source. You are pulling back morphisms, okay. It is called the pullback induced by a morphism. So F star is the pullback induced by F, okay. So it is simply G going to G circle F, okay. So this is the pullback functor, this is the pullback induced by a map, alright. And you have similar map here. So you have mod F star, which is the same as, well, this is the same as mod of F star if you want. It's not, well, probably I should not say mod of F star. So this mod F upper star, it will go from morphism as sets from y to z to morphism as sets from x to z, okay. And this is, give me any h, it will send h to, well, G circle h, sorry, h circle, I will get h circle mod f, this is what I will get, okay. This is my map. If you give me a, so mind you, h is just a morphism of sets, it is just a set theoretic map from y to z. You give me a set theoretic map from y to z, since I have a map f, since I have a map mod f from x to y, I compose it with the set theoretic map h from y to z, and I get this composition which is this, okay. And the fact is that, as you can see, that this is a subset of this. Of course maps of topological spaces are certainly maps of sets, but they are not just maps of sets, they are continuous maps, okay. And similarly this is a subset of this. Here also this set is the set of all possible maps functions from y to z, but these is a subset which consists of only the continuous functions, okay. So and you know two maps of topological spaces are equal if and only if they are equal as maps of sets, because whenever you say equality of maps you only check at the set theoretic level. Okay, so this is a subset of this, this is a subset of this. Okay, and now what I am going to do is I am going to go in the other direction. So I am going to say, suppose I have two topological spaces. So let me begin by saying the following thing: if f is a continuous map from x to y, okay, then the pullback of f induces a map from it induces a map which takes continuous functions to continuous functions. Okay, so g is a continuous function from y to z. The pullback of g, this if you want I will call this as f upper star g. This is also continuous function from x to z. Okay, so what is the so let me sum it up like this: you start with a continuous function from x to y, then the pullback induced by that takes continuous functions to continuous functions. That's what it says. Okay, now this is the model for defining what a morphism is. Okay, so the rule is, this is a very general philosophy, you want to define a certain map as a morphism, the rule is you specify that the pullback induced by that map must take good functions to good functions. Okay, so whenever you are in a situation where you know what good functions mean, so for example in the case of topological spaces, good functions are continuous functions. If you are working with for example in our case of algebraic geometry, good functions are regular functions. Okay, so you can define a morphism to be a map with the property that its pullback has the property of taking good functions to good functions. The pullback of good, so a map is a morphism if its pullback takes good functions to good functions. So this is the general philosophy, and this works, it not only works in algebraic geometry, it works everywhere. It works in analysis, it works in manifold theory, it works universally. Okay, so keeping that in mind, let's do the following thing. Let's test this. So here is a remark. So let me make that remark here. Clearly, if f from x to y is continuous, so I am abbreviating continuous to CTS, then f upper star of a continuous map is equal to a continuous map. Okay, that's what this says. F upper star of a continuous map is again a continuous map, and this is just if you want, in this case it's just a result of the fact that you know a composition of continuous maps is again continuous. There's nothing more than that. Okay, but the beautiful thing is that the converse to this statement holds, and that's the power of the statement. So here is a lemma. Let g let me write something else. Let me use phi from x to y, from mod x to mod y, be a map of sets. Okay, let phi from mod x to mod y be a map of sets. Suppose for every topological space Z, the map morphism as sets from y to z. So I should here maybe to be very strict, when I say morphism as sets, I should probably put these parallel bars to tell you that I am just looking at morphisms of sets. Okay, but you should have understood that even if I didn't put it, I am anyway taking morphism in the category of sets, so I am only worried about the underlying sets. Okay, the map from the pullback map, see, so this is the pullback map from the morphism of sets from y to z to the morphism of sets from x to z, which is given by h going to, you first apply so it's this h circle phi, okay. So the diagram is like this. So here is the underlying set of x, the underlying set of the topological space x, this is the underlying set of the topological space y, and then I have z, and this is the underlying set of the topological space z, and I have this map. If you give me a h from y to z, I have a phi from x to mod y to mod z. If you have a h set theoretic map, if you give me a set theoretic map phi from mod x to mod y, I have this composition which is just first apply phi, then apply h at this composition, okay. This is just phi upper star of h. It is a pullback map, okay. See, this pullback map, okay, has the following property. I have here a subset, I have here the subset which is morphism as topological spaces from y to z, okay. Mind you, the way I am considering this as a subset here is by associating a morphism as topological spaces from y to z as a set theoretic map from y to z, by forgetting the topological structure. I am forgetting the continuity, okay. That is how I am identifying this with a subset of that, okay. That is what these inclusions mean. When I say this is a subset of this and this is a subset of this, I am actually identifying a map with its mod here, right. So this morphism takes the map takes this into morphism of topological spaces x to z. You see, it's a property, okay. Then there exists a unique continuous map phi tilde from x to y with the associated map phi tilde at the set theoretic level to be equal to phi. So this gives you a criterion as to when a map is continuous. Suppose you give me two topological spaces x and y, and you give me a set theoretic map from x to y. That means you give me a set theoretic map from the underlying topological space of x to the underlying topological space of y. How do you check that this set theoretic map is actually a continuous map? The power of the statement is whenever it pulls back continuous functions to continuous functions, then it is automatically a continuous map, okay. So this tells you that this philosophy of defining a morphism to be a map which pulls back good functions to good functions is the right definition. It works even to define the continuity of a map between two topological spaces, okay. So this is it's a very simple observation, but it's a beautiful philosophy to work with, and it's exactly this kind of philosophy that we are going to use to define regular morphism of varieties, okay. We are going to define morphism of varieties exactly in this way. And well, so what is the proof? See, the proof is very, very simple. The proof is, well, you see, put z equal to y, okay, put z equal to y, and you put h is equal to the set theoretic map connected associated to the identity map on y, okay. So you see the diagram is that, so diagram is as follows. I have x, I have y, okay. This is this underlying set of x, this is underlying set of y, okay, and here is my phi set theoretic map, and then, well, the z I am going to put is just equal to y, so this z is just y, okay. So the underlying set of y is the same as the underlying set of z, and then the map h that I am going to take from the underlying set of y to the underlying set of z is the identity map on y, okay. And the claim is that when I do this, what I will get here is phi upper star of identity map on Y, okay. And what is the claim? The claim is that notice that identity of Y is, the identity map on Y is of course a continuous map as a map of topological spaces from Y to Y. The identity map on a topological space is always a continuous map, because after all the inverse image of a set that is open is the set itself, and that set is anyway open, so inverse image of open sets are open, therefore the identity map on a topological space is always continuous, okay. Therefore this IDY, the identity map on Y, is a continuous map of topological spaces. And so you know, and what is the conclusion? That the pullback by phi takes continuous maps to continuous maps, so it tells you that phi star of identity Y will give you a map from the underlying space of X to underlying space of Y, and that map is actually a continuous map. But what is this map? This map is this map is a map which set theoretically is the same as phi. So you know, if I set this as, if I call this as phi tilde, okay, if I so all I am trying to say is that phi tilde is actually this map, okay. So then so the proof is very clear. Since identity map on Y belongs to it's a topological map, continuous map from Y to Y, its image under phi upper star, namely phi upper star of IDY, actually lands in the set of continuous maps from X to Y with underlying map phi itself, and that is the proof. So the moral of the story is that a set theoretic map between two topological spaces is continuous if and only if it pulls back continuous functions to continuous functions, okay. A set theoretic map phi of topological spaces is a continuous map if and only if it pulls back continuous functions to continuous functions, okay. So more generally, this is the method to define a morphism. A morphism is a map such that under pullback it takes good functions to good functions. And now you know what I am going to do. How am I going to define a morphism between two varieties? The two varieties can be affine or quasi-affine, it does not matter. So what am I going to do? I am going to do the following thing. I am just going to say a map is a morphism between two varieties is a set theoretic map which pulls back good functions to good functions. And what are good functions for varieties? They are regular functions. So I am going to just say a morphism between varieties is a map of varieties, a set theoretic map of varieties that pulls back regular functions to regular functions, alright. And the beautiful thing is that there's a small glitch in this proof, in this definition. The glitch is that I have to specify for avoiding certain pathologies that the map that I start with is not just a map of sets. I should already specify that that map is already continuous, okay. So you see here what we did was the base structure, the base category was the category of sets, and the topological and the category with more structure was the topological category. So here you had, these were just sets and these were sets with a topological structure, okay. But if you go to varieties, it's even more, it's one step even more, because as far as varieties are concerned, they not only have a topology, namely the Zariski topology, but it's not just the topology that describes all the geometry of varieties. The geometry of varieties is far more higher than just the topology of varieties. Okay, to study the geometry of varieties, the first step is to study the topology of varieties. So when you look at a variety, you should look at it at 3 levels. The variety as a set is the base level, you are looking at it at the category of sets. Then the next level is you look at the variety as a topological space, in which case you are looking at it at the Zariski topology. Okay, then there is a third level, which is the variety as a variety itself. Okay, the variety as a variety itself is something more, it is not just a topological space. Okay, and therefore if you, so the point is that in that situation the philosophy, this philosophy will work. You will have to replace this forgetful functor from topological spaces to sets to the next higher level, which is from varieties to topological spaces. So what you must assume at the base is not just a map of sets, you should already assume something that is a map at the level of topological spaces. So what is the correct definition of a morphism of varieties? It is a morphism of the underlying topological spaces, namely it is a continuous map which under pullback takes regular functions to regular functions. That is the definition. Okay, so with that definition you can define what a morphism of varieties is. And all these, in all the previous lectures, whenever I said isomorphism of varieties, I meant a morphism like this. Okay, namely a continuous map that pulls back regular functions to regular functions with an inverse which also is a morphism, namely which also pulls back regular functions to regular functions. So that is the very easy definition of what an isomorphism of varieties has to be. It has to be a bijective map, and both the forward map and the reverse map should pull back regular functions to regular functions. Okay, that is what it means to say that the map is an isomorphism of varieties. Okay, and I should tell you with a word of caution that there are many categories in which usual categories in which a bijective morphism is also an isomorphism. That is, if you have a morphism which is bijective, then the inverse map is also a morphism. Okay, but it is not true with varieties, unfortunately. Okay, so for example, if you have a bijective linear map, then the inverse is automatically a linear map, so it is an isomorphism. If you have a bijective homomorphism of rings, the inverse map is automatically a homomorphism of rings, so it is an isomorphism of rings. Okay, but not all bijective morphisms are isomorphisms. For example, as I told you, I think one of these, I do not know whether I told you, but if you take the map from the real line, if you look at maps from the real line to the real line, which are with the property that they are not just continuous but with the property that they are differentiable, then you know, if you take a bijective differentiable map need not be a differentiable isomorphism, its inverse need not be differentiable. For example, if you take x going to x cube, then that map is a bijective differentiable map, but the inverse map, which is x to the 1 by 3, is not derivable at the origin. Okay, so bijective morphism never, it is not necessary that it is an isomorphism, namely the inverse map need not be a morphism. Okay, and it is also true with varieties that a bijective morphism need not be an isomorphism. Okay, so that is a word of caution, right. Okay, so I will stop here and continue next lecture.